this video we're going to be going over the basics of DC circuits. So if we have a potential difference between two locations, then this will cause charged particles to flow between the two locations until the potential difference becomes zero. So for example, positive particles like to move from an area of high potential difference to an area of low potential difference. And negative particles, including electrons, like to do the opposite. So when we have this flow of charged particles through a conductor, most often a wire, this is called electric current. And if the charged particles always move in the same direction, we say this current is a direct current. So a metal wire, on the microscopic level, it consists of a lattice, basically an array of positive metal ions and free electrons. Now, so these electrons can move around, and so normally these electrons are just bouncing around randomly, but they don't actually, there's no net movement, they just bounce around in place. However, if we apply an external electric field to this wire, then the electrons will still be bouncing around randomly, but they will accelerate, opposite the electric field, and then they have a very small net movement, and this net movement is called drift. So they want to move from the lower potential area to the higher potential area, which is opposite the electric field. So as they're bouncing around, but they're bouncing around in this general direction. And also, since the electrons are constantly bumping into the metal ions, it causes the metal ions to vibrate faster, which heats up a wire. So that's why wires heat up when a current is flowing through them. So even though in most cases in a circuit we have electrons flowing, we define electric current as in terms of the direction that a positive charge would move. And we know this is opposite to the direction that electrons actually move. So if we have a battery and a wire, the positive terminal of the battery is the area of high potential, and the negative terminal is the area of low potential. So positive charged particles, since they like to move from high to low potential, they go around the circuit this way, while negative charges, including electrons, they like to move from low to high potential, so they will flow around the circuit this way. So since we define current in terms of the direction that positive charges would move, a current in this circuit would be going this way, the same direction as the positive charges. So we calculate current based on how much electric charge passes through a cross-sectional area of the wire in a certain time interval. So let's say here's a wire, and we take this cross-sectional area, and in a certain time interval we count how many coulombs of charge pass through this area. And then so if we divide the coulombs of charge that pass through over the time interval, we get the current. And the unit of current is the ampere, which is coulombs per second. So the reason we have a battery is because it creates a constant potential difference between its terminals. Remember that normally, without a battery, the charges would flow until the potential difference becomes zero. And so once the potential difference becomes zero, the charges stop flowing. So we need a battery to maintain the potential difference. And it does this by doing work on charged particles to move them against their natural flow. For example, in this circuit up here, the electrons, they naturally want to move from low to high potential, so they go around the circuit once. But then when they're at this high potential point, they don't want to move back to their low potential. So what happens is this battery has to do work on them to get them to move back to this low potential area. And then once they're there, they naturally flow around the circuit again, back to the high potential area. So the work that a battery does per charge that moves across it is called the EMF. So the EMF is the work that the battery does on the charges divided by the charge that the battery moves across. And so the unit of EMF is joules per coulomb, or volts. So let's say we have a 9-volt battery connected to this motor. And so we want to know how the electrical potential changes as we go around the circuit from A to B to C to D back to A. So assuming we're working with positive charges, we start at A and then we go around in this direction. So from A to B, the battery needs to do work on the particles to move them from the negative to positive terminal. So as the battery does work, it increases the potential to 9 volts. And then from B to C, since this wire has some small resistance, it causes a very small drop in potential. And then the motor is the main resistor in the circuit. It's taking up energy, so there's a large drop in potential as we move from C to D. And then again from D to A, the wire causes a small drop in potential. So notice how once we get back to A, the potential is 0 again. Now this is important because we can't have multiple values of potential at a single point. It wouldn't make sense if we got back to A and the potential is like 2 or something, because when we started at A, the potential was 0. So at a single point, the potential can only have one value. So now we can start looking at some circuits. So when we draw circuit diagrams, we use these symbols to represent different circuit elements. So this straight line is a wire, and usually these wires have 0 resistance. And then here we have a battery. The longer end represents the positive terminal, while the shorter end represents the negative terminal. And then here this loop with a circle around it is a light bulb. And then this squiggly red line is a resistor. Now a resistor is basically anything that takes the electric potential energy flowing through the circuit and converts it into another energy, such as thermal energy. So an example of a resistor could be like a light bulb or something. And then we have a switch, and then these circles with an A and V are an ammeter and voltmeter. And an ammeter and voltmeter measure the current or potential difference, respectively, across its terminals. So it turns out that the current through a circuit element is directly proportional to the potential difference across it. So if we graph the current versus the potential difference for a circuit element, it'll be a straight line. And so the slope of this line, or in other words the proportionality constant, is called the conductance. And so this conductance indicates how easily charged particles flow across this circuit element. And the reciprocal of conductance, which is used more often, is resistance. And the unit of resistance is the ohm. So Ohm's law basically states this relationship between the resistance of a circuit element, the current through it, and the potential difference across it. So we have I equals delta V over R. So an element that obeys this Ohm's law is called ohmic, and one that does not is called non-ohmic. So we're mainly going to deal with circuit elements that follow Ohm's law. So there are two basic ways to connect circuit elements within a circuit. First, we can connect it in series, which means it's just one after the other. And so when we have elements connected in series, the current through each element is the same. But however, as we add more elements in series, then the total current through each of them will decrease, because as we add more, the total resistance of all these elements increases. When we have circuit elements connected in parallel, like this, then the potential difference across each element is the same. But the current through each element is not necessarily the same, based on whether or not their resistances differ. And so Joule's law gives us the rate at which a circuit element takes electric potential energy and converts it to thermal energy. In other words, the power. So we have the power is equal to the current times the potential difference across the element. And we can rewrite this law in two different ways. To do that, we just replace either I or delta V using Ohm's law. So we can get the power as I delta V, I squared or delta V squared divided by So say we have a 60 watt and a 100 watt light bulb, and we want to compare them when the potential difference across them is 120 volts. So we can calculate the resistance of the 60 watt bulb using this form of Joule's law. So we get the resistance is 240 ohms. And for the 100 watt bulb, the resistance is 144 ohms. So this bulb with a lower power has more resistance. So if we connect these two bulbs in series, remember that the current through each of them is the same. So according to this equation, this form of Joule's law, P equals I squared if we have the bulb with higher resistance, which is the 60 watt bulb, then it'll actually have more power than the other bulb, and therefore it will be brighter.